Okay, so lecture 3, homogeneous solution. The homogeneous solution, also called the complementary solution to equation 1,1. What's equation 1,1? That one, right? Equation 1,1. It's our ODE, the derivative, or the ordinary differential equation we're trying to solve. So, we're still trying to solve it. We're going to go after the first of two partial solutions that we're going to put together into the general solution. So, the homogeneous solution uses equation 1,1 still. So the homogeneous solution is the solution to equation 1,1. So the family of solutions to equation 1,1 that satisfy equation 1,1 with the forcing function f of t equal to 0, but is not restricted by the initial conditions. Okay, so we set the forcing function equal to 0. We have not yet applied the initial conditions, but we're going to satisfy what's left, which is just 3,1. So the nth time derivative of the output y plus some coefficient or constant times the n minus 1th or n minus 1st time derivative of the output y, and continue to sum all of those up. So the left-hand side is the same as it was in 1,1, and now the right-hand side, f of t, is just equal to 0. So it's kind of nice. Simplified it. What function might solve this? The homogeneous equation. So this is the homogeneous equation. We call it that. And from it, we derive the homogeneous solution. The natural exponential with base e is a good candidate since it is its own derivative, right? So for those of you who have gone through differential equations, one of the big ahas in that class is that if you take the derivative of a natural exponential, e to the t, e to the whatever t, then you get back the same thing with maybe some constant factor out front. So when you have an equation that has a bunch of time derivatives in it, and somehow they're supposed to sum up to something, a good place to start looking is that function. And that's actually where we sort of find a crack in the seam of these linear ODEs to start to find solutions. It turns out that a linear combination, or weighted sum, of linearly independent exponentials is the family of solutions we're looking for. Okay, so bonus points for those of you who got the reference. So the linear independence is actually really important. We're going to talk a little bit about it. I'm not proving that. I'm not proving that exponential is a solution either. It's good to go through those exercises, and I'm not saying that we shouldn't. I just think that this is not the place for it, because this is a primer. So presumably we've already done it. The heme team. If you get that, comment. Tell me what that reference is. Okay, so section 3.1. Characteristic equation and its roots. As the night goes on, it's just going to devolve. So I'm going to have a couple more lectures. We'll see. Characteristic equation and its roots. So it can be shown that for an exponential function, c e to the lambda t, with complex constant c and complex lambda, the latter must satisfy, so the lambda must satisfy this equation 3.2, which is called the characteristic equation. So let's break this down. It's the nth, so it's lambda raised to the nth power plus a constant lambda raised to the n minus first power. Sum them all up down to a 0 lambda to the 0, which is just 1, equals 0. So this looks a lot like 3.1, and so we can actually see the correspondence here. When you have the nth time derivative of y, you end up with a corresponding lambda to the n. The coefficients or constants end up just coming right down. And a lambda appears wherever there's a derivative. So if we have the third derivative here, we end up with lambda to the 3. So not too bad, right? Characteristic equation. Easy to find from your homogeneous equation. And another terminology thing I didn't write down, but this left-hand side here is actually called the characteristic polynomial, right? When you set it equal to 0, it becomes the characteristic equation. Before you set it equal to 0, it's the characteristic polynomial. It has n solutions or roots lambda I, okay? When these roots are all distinct, meaning none is equal to another, okay? So that's important. When all of those lambdas are distinct, lambda 1 is not equal to lambda 3, for instance. The homogeneous solution, YH, to equation 1,1 is equation 3,3. So let's take a look at this here. This is like a very important box. Fancy box. So YH is equal to sum over I of these constants, Ci, e to the lambda I t. So you're going to have a bunch of constants multiplied by e to the lambda t's. Okay. So your homogeneous solution, and I mean, we're done. So you're welcome. But there's some caveats here that we have to go back and look at. So first of all, how did we get here? We started out with the differential equation. We set the right-hand side equal to 0. Forcing function is 0. Then we said, okay, the characteristic equation then must be satisfied in lambda. So we write that down from the differential equation. Pretty easy to do from there. And then we need to solve for all of these lambdas, okay? And once we have those solved, if they're all distinct, meaning that none of the lambdas are equal to each other, we have our solution. It's just 3, 3. It's pretty easy. In fact, it doesn't get that much more complicated when we have repeated roots, which is when all the lambdas are not distinct, which is what we'll deal with in a moment. It doesn't get that much more complicated. So it's really just a little bit of an augmentation to 3, 3. So not too bad there. I mean, the homogeneous solution you will soon be able to do in your sleep. Or you probably already can. Little sips. Okay. If a root is not distinct, so if any root is not distinct, it is said to have multiplicity mu equal to the number of its instances. So if you've got 3 of them, then it has multiplicity 3. So if the same root, so if maybe one of your roots is negative 17, if you've got 3 of them at negative 17, then the root negative 17 has multiplicity 3. So if you have your normal case where you don't have any repetition, you have multiplicity 1. We typically just don't say it has any multiplicity, but technically, mathematically, it has multiplicity 1. This multiplicity causes the linear combination of exponentials to be degenerate or linearly dependent, which is what we wanted to avoid, right? We needed linearly independent, a linearly independent sum. This is easily remedied, however, by augmenting the solution of equation 3,3, so this is our old solution, with a polynomial term in T as follows. Let there be n prime distinct roots, each with multiplicity mu I. So now we've said, okay, at least one of them's got a multiplicity greater than 1, so we have to come down to this equation 3, 4. It's going to be a little bit more complicated, but not bad. There are n prime distinct ones. So maybe you've got like 3 at negative 17, and you got 1 at negative 2. So you've got n prime equals 2 distinct roots, but then you've got a multiplicity of 3 on that negative 17. So each of the multiplicities, so each of the multiplicity mu I. And if there's no multiplicity for a given root, it's mu I is just equal to 1. Okay, then the solution is equation 3-4. It's a little scary, kind of hard to parse. It's a double summation. We don't like it already. I can tell you that when I wrote this down, I was not pleased. And I thought maybe I could make this a little bit easier. But unfortunately, if you want to do this in a general equation, you're stuck with it looking a little bit gnarly. But let's parse it and let's just see how we do. I think we'll be fine. So let's take the inner sum first. So in order to take the inner sum, let's take the outer sum first, just taking one value. So I equal to 1, okay? So what we're saying this with outer loop is, the outer sum is, for each distinct root, so we'll take the first one, so I equals 1, we sum from k equals 1 to the multiplicity of that distinct root. So if it was negative 17, multiplicity would be 3, right? We have a constant that has 2 indices now down here, which is a little annoying. We got 2 indices, one for the I, one for the k. It's you know, we're in danger of getting into some sort of a terrible notation land, but we're stopping just shy of that. So it's not too bad. So some constant, it's got this double index on it. So in this first case, it would be I equals 1, k equals 1, so C11. T to the k in the first case would be 1, so t to the 0. E to the lambda. Now lambda's got to have 2 indices as well, so the 1, 1 index, t. So it's the same as this one, except now we've interpolated this t term in there, right? We've stuck the t term right in there, and we got this double sum, but really it's just about the indices. So what happens when mu is greater than 1? So if mu is equal to 1, if no multiplicity per se, then we just have t to the 0, and we recover this solution. If there's a multiplicity of greater than 1, for instance, that negative 17 root that's got triple root there, you know, in this made-up problem that we have, then you're going to sum k equals 1, k equals 2, k equals 3. So then we're going to have t and t squared showing up. So we're going to include a factor of t in the solution for a double root. And we're going to have 2 factors of t if it's a triple root, etc. And then you have to descend the polynomial and include those terms as well. Note that we would expect when all roots are distinct, the factor t in each term has exponent 0, t 0 equals 1, and we recover equation 3-3, as we already discussed. So that's that. Don't let 3-4 scare you, because we're going to do an example that has repeated roots. And we're going to see that using this double index, you can do it. Follow it. I mean, you could write this into an algorithm, a for loop. This is sort of analogous to a for loop, a double for loop. But there's really no need to be too concerned at this point as far as this equation being too complicated. We're going to see that in most cases you can simply say, oh, okay, this one's got multiplicity greater than 1. So we'll deal with that one kind of on the side here. So let's go forth and take what we've learned and apply it. So what have we done first? Let's review the bidding. So we have found the homogeneous solution to equation 1-1. Great. Which we know sums with another term to form its general solution, right? It's that particular solution we're going to add, but we haven't found that yet. We should probably consider what this homogeneous solution looks like before we move on. It's a sum of weighted complex exponential functions of time. Complex solutions to the characteristic equation 3-2, always arise in complex conjugate pairs where there's a real part plus or minus j times the imaginary part. omega in this case. So sigma plus or minus j omega, yielding terms that look like this. So you could have, for instance, have my notes on my phone here. I'm not like texting or anything, but it falls asleep. So e to the sigma plus j omega t plus e to the sigma minus j omega t. So terms like this are going to show up in the homogeneous solution when we have a complex solution to the characteristic equation. Oops, that last t was supposed to be outside of the parentheses. Okay, so let's do a little bit of shuffling around here. Each term, we can use the property of exponentials to recognize we can write each as e to the sigma times e to the sigma t times e to the j omega t. And each term has an e to the sigma in it, so we can pull that out front, e to the sigma t, and then e to the j omega t plus e to the minus j omega t. Okay? And it turns out there's this quote-unquote beautiful formula called Euler's formula that tells us that this is equal to e to the sigma t cosine omega t. Okay? The last identity is from Euler's formula. It's really cool. I recommend it. This is one form of it. Cosine theta equals, it's 1/2 e to the j theta plus e to the minus j theta. That's the form of it, but this is not the usual form that you see. This is Euler's formula. It's pretty cool, but we used it here to show that we actually have this sinusoidal term that's showing up. So this result shows us the possible forms of terms in the homogeneous solution. For a real root, so when omega equals 0, and real exponential results. So this omega being 0, cosine of 0 is 1, so we just have this exponential. Actually, the 2 goes away because this was assuming we had a complex conjugate pair, so we wouldn't have a pair in that case, right? For imaginary roots, sigma equals 0, and a sinusoid results. So for sigma equals 0, this becomes, so e to the 0, so just 1, and we just have a sinusoid. Okay? Good. And then for complex roots, so when the real and imaginary components, we say complex sometimes, and sometimes we mean that it has non-zero real and imaginary components. Sometimes we say complex meaning, as you know, of course, the real numbers are a subset of the complex numbers, so you can say complex and it could be real. That's important to keep in mind. So for complex roots, a sinusoidal oscillation with an exponential envelope occurs. So in that case, if you've got a sigma and an omega, you've got a sinusoid that has an envelope, which occurs due to this multiplication, that's exponential. So say you have a decaying exponential and you have a sinusoid, cosine, you're gonna have homogeneous solutions that look like that. Which isn't a very good rendering of that, but sinusoidal, but with an exponential envelope. So we're going to talk a lot about this kind of thing in the coming year in mechatronics and system dynamics, but we're laying this foundation here. Even when we look at the mathematical form, we're going to see all of these characteristics arise, and we've had access to them since we've been able to solve differential equations, but we might not have recognized that they were important until now. So, okay. Everything we know about the exponential also applies. So like I said, if sigma is less than 0, an exponential decay results, whereas if it's greater than 0, an exponential growth occurs. So the envelope need not necessarily decrease. And that has a lot of implications if you have a dynamic system that has a response that grows over time. We're going to have a name for that. It's going to be an unstable system. So lots of fun stuff. So let's do an example. A homogeneous solution. Find the homogeneous solution for the equation with this fifth order equation. So fifth time derivative of y looks pretty intimidating. I mean, I made this problem, a fifth order problem, and guess what? There is going to be repeated root in there. Just to show that even something that looks as complicated as this is really not too bad. So, find the homogeneous solution for this equation. So, what's our first step? We're going to find the characteristic equation, right? That's our first step. So, the characteristic equation is, we have the fifth time derivative of y, so that gives us a lambda to the 5 plus 14 times the fourth time derivative of y, which translates into the fourth power of lambda, plus 81. The third time derivative of y means the third power of lambda, plus 248. It's almost getting boring at this point, right? We just are repeating the same thing over and over again. And 408 lambda plus 288. And then lambda to the 0, because of 0 time derivatives here. So lambda to the 0th power gives you just 1. And we are going to set that equal to 0. We could have written down the homogeneous equation with f of t set to 0, but it's really an unnecessary step. We're just saying, okay, for the homogeneous solution, we set that to 0. Okay. Now, you need to solve this for lambda, right? Solve for lambda. Fifth order, so there's no, so we have the, quadratic equation, which does that for a second order system for us analytically. Can go up to a third, fourth. I think there might be a fifth. I can't remember if they've actually come up with a solution, but even when you get to third and fourth, the expressions are humongous. So in general, we don't do this analytically for a higher order system. What we do is we use a numerical root finder. So we're finding the roots, right? The roots of a polynomial being the values of lambda for which the polynomial is equal to 0. So a root finder, such as probably our favorite is MATLAB. Okay. Could use Mathematica or sort of similarly Wolfram Alpha by the same company. That one's free, but Mathematica is free in our labs. Or Python or whatever the programming language. A lot of them can do this. Another option though is actually your graphing calculator. So there are also some times when you can look at it and see things you can divide out, factor out. There are some people who will teach that as a method. Maybe you do it in differential equations. Great, if you can recognize it, that's cool. There's no need, though, in this class to be able to do that by hand for anything higher than a second order system. So, favorite root finder, and it's going to give you these lambdas, and it's in an arbitrary order, okay? So we're going to we can number them however we want. So I'm going to say, now, we're going to end up with repeated roots. So one of the roots is repeated, as we'll see in a moment. So that means we have to use double indices for it. So we don't have to, but we're going to this first time, and then we'll discuss how we can maybe avoid doing that in the future. So lambda 1, 1 is -4. So this just came, actually I didn't use a root finder because I constructed this polynomial from multiplying something out, so I knew the roots a priori, as Kant would say. You guys really need to do philosophy. Philosophy is pretty badass. Okay, so lambda 2, 1 and lambda 2, 2, this is going to be the repeated root of -3. So we're going to say lambda 2, 1 is -3, also lambda 2, 2 is -3. So the first index we're using for denoting it's a distinct root, -3, but there are two of them, so you have a 1 version and a 2 version. Okay, and then we also have lambda 3, 1, which is -2 plus j2. And I said earlier that whenever we have complex roots, they show up in complex conjugate pairs, right? So lambda 4, 1 is equal to -2 minus j2. So there's our complex conjugate pair. So this is not a repeated root because these are distinct, right? They have different imaginary parts. But these two are both -3, so we could write -3 comma -3 if we want to make sure that we saw that there were two. Okay. So the first one is a real root. The second one is a repeated real root. So it's real, but it's repeated. And then the third one, they're distinct, but they're the third one and fourth one are complex conjugates. So it's a pair. So the homogeneous solution a la equation 3, 4, so say that, from equation 3, 4, we know that y, let me start this over here, y homogeneous of t, so we have to use the more complicated expression. So we'll rewrite it. So from I equals 1 to n prime. What is n prime? So we have 4 distinct roots, right? So I equal 1 to 4. And then we have the sum from k equals 1 to, and then we're just going to have to leave this as mu I, okay? Because that actually depends on which I we've got. So you can say mu1 is equal to, what's the multiplicity of lambda 1, 1? There's only one of them, right? So multiplicity 1. Mu2 has multiplicity, so this one, there's 2 of them, right? So multiplicity 2. This one is distinct, so multiplicity is 1, and same with this one, multiplicity 1. So that'll go in this inner summation when I changes. Then we've got our C I k e to the k minus 1 times t times e to the lambda I k t. Okay, so let's go through this. We've got when I equals 1, we have c1. So when I equals 1, we're talking about this root. So it's distinct multiplicity 1, so mu I is 1. So the sum from k equals 1 to 1, so k is just equal to 1. So we have c11 e to the k is 1, right? So e to the 0 t. Oh, pardon me. I have made this horrible mistake. This is not e raised to the power. It's t raised to the power of k minus 1, right? It's not bad. So we don't have this. We have t raised to the power of k minus 1, in this case, is 1 minus 1, or 0. And then we've got plus, oh no, not plus yet, e to the lambda 1, 1 t, plus, now we've got I equals 2, so c 2, 1. And first we have k equal to 1, right? So first k equals 1. So we're going to have t to the 1 minus 1 e to the lambda 2, 1 t plus, now we do have mu I, that's 2 in this case, right? So now we've got 2 here, so k equals 2. So c c2 2 now t raised to the k, which is 2 minus 1, so now this survives, e to the lambda 2 t. Good. So this is our repeated root. We dealt with it. So now we've got plus, the next term is this 3, 1 case. So now we've got c3, 1 t raised to the 1 minus 1. So k is equal to 1. Mu I, so mu 3 is 1, so that's all we've got for this. And we've got e to the lambda 3, 1, because it's a distinct root. And then finally the other half of this conjugate pair is 4, 1 t to the 1 minus 1 e to the lambda 4, 1 t, which simplifies, right? So the t to the 1 minus 1 is just t to the 0, or just 1, right? So let's rewrite that as c11 e to the lambda 1, 1 t plus c21 e to the lambda 2, 1 t plus c22, here's the repetition that's happening. So now we've got the t to the 2 minus 1, which is just 1, right? So t to the 1, or just t, e to the lambda 2, 2t plus c31 t to the 0, or just 1, e to the lambda 3, 1 t plus c41 e to the lambda 4, 1 t. Okay, wonderful. We could plug in lambda 1, 1, lambda 2, 1, etc. if we wanted to. That would be totally fine. I did want to mention though, so this, using the two indices thing and going back to the summation formula, it's kind of tedious, and I actually think we would probably do best if we said, okay, if we have repeated roots, let's identify them. If there's like multiple repeated roots, maybe we will go back to this formula. But notice where we ended up. We ended up with a constant times e to the lambda t, another constant times e to the lambda t, another constant times e to the lambda t. But since this was a repeated root, the second one's got to have a t in it. And the other distinct roots all show up as c e to the lambda t. So these all of the terms other than the repeated terms look just like this original one, constant times e to the lambda t. So what I recommend doing is just saying, okay, whenever I've got a repeated one, I have to write down a copy, so in this case it's multiplicity 2, so I had to write 2 terms, but if you have multiplicity 3, you'd have to write 3 terms, etc. And the first one doesn't get a t. The next one gets a t. The one after that gets a t squared. And then you just keep adding 1 to the exponent as you go along till you've reached the full multiplicity. Okay? So that's how I would recommend doing it. It's up to you. You can go back to the formula if you're most comfortable, but I would say that you need to become pretty comfortable doing this, so you should be able to do it pretty quickly. Going back to this formula, first couple times is good, but then I think you really need to move beyond that and be able to do it more quickly and still not make any mistakes. So, okay, that is all for the homogeneous solution. So we've found this homogeneous solution. We've done an example of it. I'll just talk about the exercises for just a moment. So this is the first lecture that has exercises, this, and then the final 2 lectures also have exercises. So all of the answers for these exercises are in the appendix. So you can see the answers. They're not full solutions, they're just answers. So you can check your work. And they're all using this sort of strange form. I see a typo here. Find the homogeneous solution, YH, and I'll fix that on the online copy. For equation 1, with the order n and coefficients ai given. So equation 1, going back to this guy here, what we're saying is, given these a's, so we're making this specific, right? And given n equals 2. So I'll do the first one with you. I'll write the first one down. I'll let you solve the differential equation. But second order differential equation. So we already know that this thing has to have the form d2y dt squared. So the second time derivative of y, it would be plus, but there's a negative 1 here for a 1. So we're going to say minus 1 times the first time derivative of y. And then a 0 is negative 2. So minus 2, and then the 0th time derivative is just y. Okay? And it equals f of t. But we're just finding the homogeneous solution, so we'll be setting that to 0 for the homogeneous solution. Okay? So that's the first one, and then the rest of these you can do on your own. Not just write the equation, of course, now we want to find the homogeneous solution. So the answers are in the back, and best of luck to you. All right, cheers.